Okay, welcome to the afternoon session, everybody. So welcome, Your Highness, and thank you for being with us. The first speaker this afternoon is Professor Tony Cheetham, and I call on you, Tony, to give your talk, and then after that we will have a ceremony. So I'm going to delay my remarks until after you've spoken, okay? So please come ahead. And Tony's going to tell us about how materials are discovered. Please.
Your Highness, Excellencies, dear friends, ladies and gentlemen, and all the people out in other countries who are listening online. This is an exciting moment for me, and I've been looking forward to it for quite a long time. The challenge was to design a talk that will keep His Highness's attention for the next sort of 45 minutes or so, whilst not giving the impression to my colleagues that I have lost the plot and no longer doing any exciting research. And so I'm going to try to strike a balance. I shall also be striking a balance between things I've done myself and things over my career and things that other people have done that have impacted us. So I called it How New Materials Are Discovered, and I'll just give you a little bit of an introduction. It's dedicated to His Highness Sheikh Saud for his 15 years of incredible generosity and support for RACCAM and this international workshop, and which was launched in 2007. And I have many photos. I picked one, Your Highness, from the very first event in 2007, our launch of RACCAM. And I realized that I had hair in those days, and also it was not quite as grey as it is now. You look somewhat older here, Your Highness, than you do today. But that's a wonderful picture from the launch of RACCAM in 2007. But we're here to talk about materials, and materials are not new. I wanted to emphasize that. Materials are not new, and I've just given a few examples over the years of this Bronze Age sword, which is 3,500 years old, the terracotta warriors from Xi'an in China, and the Lycurgus cup, which is in the British Museum, but was made in Rome, and that's from about 300 AD. And then a book in the 1550s on extractive metallurgy. It's amazing that people are writing books on extractive metallurgy 500 years ago. And these materials are still important today in that they represent metals, they represent ceramics, they represent glass. And this Lycurgus cup is especially interesting because it has nanoparticles of silver and even a little bit of gold in it, which enable it to have particularly interesting optical properties. But here we are today. It's the 21st century, and we have a lot of challenges for the 21st century: the population, aging, energy, environment. We all know these challenges, these global challenges. And the key point I wanted to make here is that materials have an impact on most of these areas. I'm not quite sure about population and aging, but I'm sure people would have ideas on that, maybe you, Your Highness. But in all the other cases, clearly material science and new materials play a role in improving our energy situation, protecting the environment, health and security, and so on. So let's just look at some of the materials that we have in everyday life. Of course, we're all familiar with construction materials, and there's wonderful business here in Rasselheimer with Stevin rock and Rack rock that contributes to that. But then, you know, we have our mobile phones, the internet, which depends on materials, our personal computers, things that we take for granted, which are full of materials, transportation, solar panels, wind farms, LED lighting, health and medicine like this MRI scanner, NMR type scanning, which depends critically on materials. One of my favorites here is the Dreamliner, and the Dreamliner's made from 50% carbon reinforced polymers, so it's basically kind of organic. And if you look at the picture here, you can see the parts in grey are the parts that are from the polymer composite. So it's about 50% polymer composite, which makes it 20% lighter than an equivalent aircraft made from aluminum. And so ironically, even though it's much lighter, the body's stronger than the conventional aircrafts. Because it's much lighter, the fuel efficiency is better, and so it can go about 20% further. So that's why we can fly on a Dreamliner or an Airbus 350 for 17 hours or so across the world. And another exciting thing, because it's stronger, you can pressurize it at, as if you're at 6,000 feet rather than 8,000 feet. So it's a lot more comfortable. You don't have altitude problems. And because it's made of polymer carbon composites, it doesn't suffer from corrosion as much. So you can keep the humidity higher. So the humidity's about 15% compared with 4% if you go on, say, a 777 or even an Airbus 380. So you'll notice if you're doing an overnight flight, it's much more comfortable when you arrive. And then there are lots of other interesting technologies, smart windows, solid-state lighting. Here I am in the captain's seat of the Dreamliner, and you can see the heads-up display there in pink, so that you know, technology of heads-up display, lithium-ion batteries, air purification, all built into this amazing aircraft. So when you think about materials, you have to remember, of course, that everything is made of elements. And so we all know the iconic periodic table with about 100 usable elements, for just roughly speaking. And if I take my iPhone, for example, or any smartphone, there are, according to one report, it said there were 46 elements in it. I know at least 2 elements that are not on this list here. So if we say that there are about 50 elements in the various components of the iPhone, then it basically uses half of the periodic table, which is an amazing fact. And these are some of the things that it uses, like the lithium transition metal oxides for the batteries, and tantalum and zirconium oxides, indium tin oxide for the touch screen, and so on. Neodymium for the magnets, and so on. This cerium into the yttrium aluminum oxide for the phosphors is the one that's not on the list there, because it's responsible for the LED light that you can use on your iPhone. So materials have an incredible impact on our life, which most people are kind of totally unaware of this, and how many things have changed over the last decades. And I just put together some of the major discoveries in materials over the last 40 years. And we have the things like the lithium-ion batteries, which I'll talk about in a bit more detail, and conducting polymers. People remember the discovery of high-temperature superconductors in 1986. I'll talk about the carbons and graphene, of course, and I'm thrilled to see Andre Geim in the audience here, who got the Nobel Prize for getting discovering graphene, wearing his graphene pants today. And So all of these cases have been honored with Nobel Prizes. I like the quantum dots. These quantum dots here, Your Highness, they're all the same material. They're all basically cadmium selenide. And just by changing the size of the particles, you can change the color of them when you put them under, say, UV light. So the chemistry is the same, but the size is different. So there've been a huge number of important materials advances. This is kind of never ending, and this is just a sort of representative but important list. So some of the questions I wanted to look at, I've been thinking about this since last summer, was how do such discoveries take place? What's the anatomy of a discovery of this talk? What's the timeline of materials discoveries? And where will tomorrow's discoveries come from? What do we need to be doing today so that we can make the advances that are required tomorrow? And so I've been thinking about this with Ramsa Chaudhry, who's sitting over at the back here, who's attending the meeting, one of my colleagues from Santa Barbara, and also Fred Woodle, who's not actually here, but he's going to be in a photo in a few minutes. And we spent several months agonizing over these questions and trying to distill from all the information we had some of the general trends that emerge. And so we just submitted it to Nature's Synthesis. If they don't want to publish it, I don't care. We'll send it somewhere else. It doesn't matter. So I'll tell you where we sent it to. This is a new journal. So one of the things that we did was put together some timelines for discovery. And you won't be able to see all the details here on the left. But these lines represent at the left-hand end. So if you go, I don't know, if you go to the lithium cobalt batteries, this is where the lithium cobalt oxide was discovered. And then this is when, as it were, the light went on and people realized that this could be incredibly useful. That's in green. And then this sort of ribbon here is when it got some major recognition. In this case, it was the Nobel Prize. So what are the points that you can take from this without going into any of the details? One is that the materials breakthrough, which in this case was the cathode for the lithium-ion battery, often follows or is preceded by the synthesis of a new chemical compound. So laboratory synthesis is important. And that there's a time lag between those events, not always, but nearly always, and it's several decades. This is why you shouldn't invest in brand new materials, Your Highness, because the time to market is extremely long, as this chart shows. The reason for the original synthesis at the left-hand end is nearly always totally different from where it has an impact later. And in fact, sometimes there was no reason for it other than pure curiosity, which I want to talk a bit more about. And finally, not all of the discoveries work in this way. Sometimes a discovery is about a new form of an old material. And in a way, Sir Andre's graphene is an example of that, because graphite has been known, as long as only 500. But I would claim, with due respect, sir, that it's been sort of dug out of the ground in China even longer than that, because it does occur naturally. And well, let's just agree it's 500 years. We don't to argue over a couple of centuries. So sometimes, and so then what Sir Andre did was take something which was known as graphite and then create it in a new nano form, in this case a single sheet of that structure, and totally transform the properties in an incredibly exciting way. So what we found in reviewing all of these things, and that's just, that chart just shows a small sample. We looked at all sorts of things, and I know there's everybody looking at the paper that we're going to publish or listening to this talk will be saying, why didn't he talk about such and such? You know, that would be interesting. And everybody will have their own ideas. But there are basically three common pathways here. One is pure serendipity. Something's found that's totally unexpected. And that's the case, for example, in the Buckyball, which I'll talk about, and also with the discovery of Teflon at DuPont, which I won't have time to talk about, which is a fascinating story in its own right. Or the discovery was made using design principles based on learnings from previous work. This is what the funding agencies love, because they want you to think that you know what you're doing, and you're going to take all the understanding that we have out there and extend it using the principles from the earlier work. And I'll give one example of that concerning zeolite catalysts. And then the third is that you take something that's already known and you, for want of a better word, you repurpose it for some new application. Or maybe there was never an application before. So it's repurposed for a new and exciting application. And the lithium-ion battery cathode is a really nice example of that. So the thing is, when you look at it, and this is what slightly surprised us, serendipity is really rare. You don't want to be relying on serendipity. Discovery using design principles is also rare in terms of really game-changing discoveries. And repurposing of something we already know is by far the most common example. So let's take the Buckyball C60, and this morning I constructed this model of C60. So this, Your Highness, is a sort of football type sphere, falling apart, of 60 carbon atoms that was discovered in 1985, and I'll say a little bit about that, by my old friend Harry Kroto, late friend Harry Kroto, Rick Smalley, who also passed away, and Bob Curl, and they were working together at Rice University, and they shared the Nobel Prize about 10 years later. And here's their paper, and they recognized at the time that this molecule was basically the shape of a football. And the context of that, of course, is that the other forms of carbon that everybody knew about were the graphite, which was used in pencils. You know, that's what you use for pencils, amongst other things. And diamond, of course, which has been known a very long time. And suddenly, you have an entirely new form of carbon. I made that for you this morning, Your Highness, so you can keep it. And I've also put a kit here, Your Highness, so that you could try and make it yourself later, and which is a little bit tricky. So let's look at the anatomy of this discovery of the Buckyball. Serendipity and the Buckyball. So the idea of hollow carbon molecules like the Buckyball was suggested tongue-in-cheek by a scientist called David Jones, who used to write in the New Scientist in the 60s. And he used to write under the sort of nom de plume of Daedalus. And he just floated the idea you could have hollow carbon molecules like that. And then there was some theoretical work in Japan in the 70s, which predicted, amongst other things, that there could be a stable aromatic cage. And my chemistry colleagues will know what aromaticity is. It gives it special stability. But that was just theoretical prediction. Then the year before it was actually discovered, the group at Exxon, 1984, group with Kaldor and his colleagues, studying soots from hydrocarbon cracking catalysts, because they're interested, what's the nature of the soot that you get building up on the hydrocarbon cracking catalyst? And they used mass spectrometry, and this is a spectrum that they got the year before the discovery. And if you look carefully at it, I put a star here. If they'd been super percipient, super observant, they would have wondered, why is this star at C60, and all the ones to the left are lighter, like C20 or whatever, the ones to the right are heavier. Why is that peak bigger than the others? Maybe they did wonder that, but they also looked, oh, well, there's a big one at 70, and then there are other ones down here. So they didn't make anything of it. A year later, in Rice University, with Harry Kroto and his colleagues, they did the experiment a different way. They took a piece of graphite, bombarded it with a laser, sort of ablated carbon species into the gas phase, and then, depending on how they observed them and how they allowed them to equilibrate, they got different spectra. And you can see that C60 with the red star. If you're really careful and you don't allow them to equilibrate, you see that the C60 turns out to be the dominant species. And also the C70 there, which was apparent here. And so that's what led to the paper that I showed here, which was published in 1985. So there was already indications there, but they had the wit to recognize that there was something special going on here. And this was an incredible breakthrough because it was a new form of carbon. And here it is, like the model I just gave His Highness. This is Sir Harry Kroto and his wife Marg there. This is Fred Woodle, who's been working on the paper for Nature Synthesis with me. And that's me. We were at the Royal Society, at a Royal Society soiree in London in about, I don't know, 2010 or something like that. But the irony is that even though the Buckyball made a huge splash, in a way it didn't have any commercial impact, or very little commercial impact. But what it did do was spawn a lot of interest in other nanoforms of carbon. So if you can make C60 in balls, could you make tubes? And so Endo and Iwajima in Japan both made carbon nanotubes, which was recognized at the Kavli Prize for Iwajima in sort of 15 years ago or so. So these are basically like the Buckyball. If you take a Buckyball, cut it in half, and then roll up one of Andre's graphene sheets and cap the ends, then you've got a carbon nanotube. And then, of course, there was the discovery of graphene that followed it. And here's a lovely picture of Andrei and Kostya Novoselov, with whom he shared the Nobel Prize. So what was important about C60 in the end was primarily that it spawned all these other exciting things, which in terms of commercial potential are actually arguably much better than the original Buckyball. But it also, to my mind, it launched the nanomaterials revolution, because people started to think, maybe you can make nanoparticles out of virtually anything, like those quantum dots I showed earlier with the different colors. And so that's been an incredible story. There's one other facet to it. Harry Kroto and his friends were making it in the gas phase. And of course, you couldn't really use it for anything. But then there was another team, Kretschmer and Huffman, about 6 years later, who figured out how to make it as a solid. And then that did lead some interesting physics, interesting chemistry, but not a lot of particularly sort of impactful materials applications. So that's an example of serendipity. What they were looking for at the time when they discovered the Buckyball, they're trying to simulate the conditions that are in interstellar space, because Harry'd been interested in small carbon molecules, and carbon-12, the carbon-12 isotope's incredibly stable, so it's one of the first things that forms in the evolution of the universe as smaller particles condense to form atoms. And so they were looking for that, and they found C60. Since then, it's been shown that C60 actually does exist in interstellar space. So it's shown by a guy called John Meyer from Switzerland. So let's turn to materials by design. And this is a bit complicated. I'll try and make it simple. These are aluminosilicate zeolites. And so they're basically different forms of sand, if you like. And sand is silicon dioxide or silica. And these have got some aluminum in them. So you have a framework of silicon and aluminum and oxygen. And then just to make all the charges balance nicely, you have cations. And the cations might be metals. It might be a metal, or it might be an amine, or it might be a proton, a hydrogen ion. And what's interesting about these aluminosilicate zeolites is that they occur in nature. And so there are a large number of different forms in nature. And then you can also make them in the lab as well. Some of the ones that occur in nature don't occur in the lab, and vice versa. Some can be made in the lab and also occur in nature. And there are about 50 different architectures here. And what they have in common is that they've all got channels, like so, of roughly molecular dimensions for small molecules like benzene. And so you can use them as molecular sieves. And so the question is, if we want to use them as a sieve for a particular application, how do we control the size of the cavities and get the architecture of the molecular sieve that we want for a particular application? And so that problem was originally solved by my academic grandfather, Richard Barra, who was at Imperial College. And he did this work in about 60 years ago and showed that you could use amine templates, just small amine cations that get trapped in the cavities. And if you use a little cation, you get a little cavity. If you use a big cation, you get a big cavity. And so that was well known. And then, so that's the design principle. And then people have extended it. And this is sufficiently important in the oil and gas world that, companies like Exxon and Mobil and BP, etc., would have research teams that worked on making different zeolite architectures and different catalysts. And I think the two most exciting discoveries, to my mind, one was a group at Mobil who used tetrapropyl ammonium, which is quite a large cation, so it makes a big cavity. And then you can burn it out afterwards to create the catalyst. And that turned out to be a key material for two applications. One is xylene isomerization for making paraxylene, which goes into polyesters. And the other is as an important component of cracking catalysts for gasoline manufacture. And Natalie is an expert in this area, and so I consulted her about this. The other really exciting and sort of somewhat different application of this design principle was to use a really big amine cation, like a surfactant cation, with long chains and so on. And if you do that, you get huge cavities, not just molecular size, they're very large cavities. And these are called mesoporous silicas, and this was discovered at Mobil, as was the ZSM5, this in 1978, this in 1992. And so this strategy is still being used today. And when we were doing the article, I found articles, very recent, interesting articles where people have used this principle in a variety of different chemistries, not just aluminosilicates, but with aluminum phosphates and germanosilicates and so on. So this is the mesoporous silica, where you use these large surfactant cations, and they kind of self-assemble into tubes, and then the silica condenses around them. And then you can burn the surfactants out afterwards, and you get these porous structures. They're like, looks somewhat like the carbon nanotubes, the sort of collection of carbon nanotubes I showed you earlier. But these are the holes. This is from the original paper showing you can actually see in the electron microscope, you can see the holes there. Let me turn to the third strategy now with the repurposing. And I wanted to talk about lithium-ion batteries, and that was celebrated a couple of years ago with a Nobel Prize in Chemistry for John Goodenough here, and Stan Whittingham, and Professor Yoshino in Japan. And John Goodenough is a very old friend of mine. In fact, I dug out this photo you see on the left. In about 1976, when I was a young academic at Oxford, he came to Oxford from the States as the head of inorganic chemistry. And we have this lovely photo. This is John today. He will be 100 this year, and he's still publishing and still going strong. This is John in the 1970s, and this is me in the 1970s with plenty of dark hair and so on, and these are all my colleagues. This was before the discovery of the battery cathodes that John worked on. But now on the wall, just behind where we're all standing here in 1975 or something like that, there's a plaque on the wall celebrating the discovery of the cathodes, which we have in our batteries in cell phones and so on. So the whole idea, of course, of using batteries, it seems very modern, and I'm going to talk about electric vehicles, but I wanted to remind everybody, some of you might not know this, that electric vehicles are not new. And the first electric vehicles were developed in the late 1890s, so like 120 years ago. And this one here, I saw this in a museum in Florida, and it's a Baker electric car from 1908. And it has some familiar problems. It has a range of about 50 to 60 kilometers, which is a bit of a problem. Top speed of 30 kilometers an hour. And so, of course, when people realized that you could run a car with a gasoline engine instead, and you could top it up in minutes and go for much further at higher speeds, these kind of dinosaurs went out of fashion. But they were mass-produced for a period, and then Henry Ford started to mass-produce the gasoline vehicles and put them out of business. But of course, they've made a return. And the first case was a hybrid where you've got both a gasoline and an electric motor. And the electric motor for the first Chevy Volt was not much different from the one I've just shown you from 100 years ago. You know, it had a range of 35 miles. It had, because it has a gasoline engine as well, it could go faster and it could go further if you use the gasoline. But the electric vehicle part of it was roughly the same. And then the next generation had a new battery with a range of about 85 kilometers, 50 miles or so. But it took about 5 hours to charge if you plug it into your electricity in the USA, where you've only got 110 volts, it takes a long time to charge it. And so this picture here shows the magnitude of the problem with the electric vehicle, because this is the CEO of General Motors, who you can see is a very large man. And this is the first battery that went in the Chevy Volt that would take you 35 miles. And this is significant. This is a 400-pound battery, or nearly 200 kilo battery, and you only get 35 miles out of it. So it shows the magnitude of the challenge here. What Tesla did, and people will be familiar with the Tesla car, this is a Tesla S, they said, okay, we need a lot of battery here. So they made the whole of the chassis, this whole part here, is battery. So when you get in the Tesla, you're sitting on top of the battery, and so are the people in the back of the car and so on. You have a huge battery. And they've used different generations of lithium-ion batteries. This now has a range of up to, the latest versions have a range of up to about 400 miles, 600 kilometers. charging takes several hours at home, even if you've got say a 220-volt charging system, but with supercharging stations that are sort of popping up everywhere in the USA and many other countries, you can charge in about 30 minutes. And so the amazing thing about the Tesla S, it will go from 0 to 60 miles an hour, or 0 to 100 kilometers an hour, in about 2 seconds, which is just a stunning acceleration. So I'll just say just a bit of science, that the battery has several components. It's got electrodes, a cathode and an anode on the left. It's got an electrolyte, which might be a solution or a polymer or a solid. And then there's normally a separator in the middle as well to stop things going from one side to the other that you don't want to do that. So these are the 4 components. And when you look at the lithium-ion battery, they're all based on things that were known before. So none of these components in most of the lithium-ion batteries are new. And so the lithium-ion battery was initially launched in the period 1978 to 1980. And the important cathode is lithium cobalt oxide and derivatives of that, by no means the only one. Stan Whittingham, who was also at Oxford in the laboratory I showed, he was about 2 years ahead of me, who got the Nobel Prize. He was working at Exxon. He proposed a sulfide-based battery, not an oxide. And 2 years later, John Goodenough said, no, we'd do better with oxides because oxides will give us more energy capacity, so they'll give us more miles and better stability. And so this is a paper, this is a key paper from John Goodenough's work in 1980 when he was at Oxford. For those of you who are looking online from far away, you'll see that this was published in Materials Research Bulletin, not in Nature X, but it still went on to get him a Nobel Prize. And so the cathode's based on this lithium cobalt oxide, which is a kind of layered structure where the lithiums, the little balls here that are lithiums, they can go in and out of the structure as you charge and discharge the battery. Compounds based on that are still used today. And the issue is that people don't want to use lithium cobalt oxide because most of the cobalt comes from the Congo. And there are all sorts of geopolitical issues. You know, cobalt is toxic. It's mined in rather difficult conditions, should we say, without quite as much attention to health and safety as you might expect. And recently, Chinese companies have bought most of the cobalt mines in the Congo. And so they have some control over cobalt. But because of the toxicity and cost issues and the other issues, people want to get away from cobalt. But it's often the case that you know, the first one that you discover might turn out to be really excellent, but then you find all sorts of reasons why it's not ideal. And so they've been using this same framework here, but replacing cobalt with nickel and manganese and getting as much nickel and manganese as you can whilst sustaining as much performance as you can. So the amount of cobalt going into them now is actually quite small. So that's the story of the cathode. But if you look at the history of the cathode, it was originally, this lithium cobalt oxide, it was originally made for a totally different reason. And it was made about 30 years before John Goodenough's work, where he made a battery out of it. And it was made out of curiosity, really. And then people looked at the magnetic properties and so on. And then a few decades later, it turned out to be particularly interesting. So for the people online, there's a really nice review by Mantharam from UT Austin in Nature Communications about the new cathodes. There are other ones like lithium iron phosphates and so on, which are also being explored. This was also developed by John Goodenough. Again, this had been known since the 1950s. but long prior to the idea of a rechargeable lithium battery. So I want to focus on another thing now. There are lots of cathodes, actually, though these lithium cobalt oxide related ones are very important. But in terms of anodes, the other side of the battery, there are really only two players at the moment. One of them is the graphite that we talked about earlier. There's an extensive use of graphite, which occurs naturally and mainly in China. But there's also a relatively new one, a lithium titanium oxide, which has some sort of superior properties to graphite, and it's known as LTO. And then very recently, there's the development of a third anode based upon titanium niobium oxide. And this is another example of repurposing. So the titanium niobium oxide, here's the structure of it, it doesn't really matter, but it was first made in labs in the USA in the 1950s, and people were interested in ceramics for the nuclear industry. And so there's a paper, 1955, about that, and then the structure of it wasn't known, the crystal structure, but then the crystal structure was basically determined in 1961, just a few years later, by David Wadsley in Australia. And he assumed that the niobium and titanium were kind of randomly distributed in this structure in each of the different cation sites. And then a couple of young guys at Oxford, Bob Von Driel and Tony Cheetham, looked at this and thought, we could do a better job on that because we don't believe that the titanium and niobium are random. And so we used a very new method at the time, which is called the Rietveld method, which some of the people in the audience will know about it, which was only sort of launched in 1969 for refining complex structures with powder data. So this is our paper in 1974, determining the structures of the titanium niobium oxides, TiMb207, and another more complex one. And our interest in this was to demonstrate that this new Rietveld method was capable of refining an incredibly complex structure. And in doing so, we found that the titanium and niobiums were not at all randomly distributed, but they were segregated in different sites within the structure. And much later, that turned out to be important. So this was in 1974. We were not thinking of lithium-ion batteries because the lithium-ion battery hadn't been discovered or thought about at that point. So just if we look at that previous slide, what we've done here is refined and sort of improved the solution to a known structure that the X-ray people had done. About a decade later, just as a segue, we showed that you could use these powder techniques, and this might be one of the reasons I'm here talking to you today, because we showed that you could not only refine structures, but you could also solve totally unknown structures from powder data. And we did it both with very high resolution neutron data, which I'm showing here, and also with very high resolution synchrotron data as well. So this is just a short segue. We chose this iron arsenate, which was, of unknown structure at the time. The reason I wanted to show you this is that this caught the attention of Linus Pauling. And Linus Pauling wrote to me, and it starts off very well. I've read with great pleasure your paper on the crystal structure of ferric arsenate. And then he says, you mentioned some examples of five-coordinated iron in the oxide structure. Then he gets to the point. If my memory's correct, I actually found five-coordinated iron in 1930, basically, and you didn't cite me, is what he's saying. And he said, I'm not absolutely sure. However, when I get an opportunity, I'll check this point and perhaps send another note. So I immediately went into the library and looked at this paper, which he couldn't find, his old paper. And in Oxford, we had a fabulous library for old papers. And I found the paper and found that he got muddled up. And it was not five coordinated like our compound, it was 4 and 6. And over the sort of decades, he'd kind of averaged 4 and 6 and thought it was 5. And then he wrote to me. He was obviously slightly sort of perturbed by this. So he finally found the paper, and then he wrote to me about 3 weeks later saying, actually, I've just checked it, and I'm wrong. But the other thing, and I love this last thing at the end, he said, I'd also like to make another comment, that you mentioned that the edge shared between two of the iron polyhedra, this oxygen-oxygen distance, is 2.38 angstroms. I'll put this into context. I think that it's likely that this edge is, so 2.38 is nearly 2.4 angstroms. He thinks it's 2.5, as discussed on page 561 and 562 of my book, The Nature of the Chemical Bond. So Linus Pauling was worrying about the possibility that this distance between two oxygen atoms might be 1/100th of an angstrom in error. And 1/100th of an angstrom, Your Highness, is like 1/1000th of a centimeter. And it's exactly 1/1000th of a centimeter. And so I love this because he was about 85 years old. And yet he still had this great passion, and he was obviously fired up because we'd not referred to his work and so on. But it's a wonderful story. So let's go back to the anode. This is just a segue, this titanium niobium oxide. So we'd looked at it in '74. Then in 1980, John Goodenough and others basically launched the rechargeable lithium battery. But this was not a candidate to use in the battery at the time. But then in '83, a few years later, Bob Carver and colleagues at Bell Labs showed that you could actually put lithium into the channels of this structure. You could insert lithium. And that's where my titanium niobium distribution became important, because it has an impact on the lithium diffusivity. And then another nearly 30 years later, John Goodenough again pops up, and he shows that this titanium niobium oxide works really well as an anode in the lithium-ion batteries. And that was published in Chemistry and Materials. So now, another decade on, these things take a while. This is being commercialized, finally being commercialized in a collaboration between Toshiba and a Brazilian mining company, CBMM. And what's interesting about that, in a way, is that niobium's quite an expensive element. So people thought, you're never going to make a battery anode with niobium as a major component. But the major niobium producers saw this as a new market for themselves. And so they've worked closely with Toshiba to make this possible. And so what we did last year, this was published in 2021, we got together those who'd worked on this problem who were still alive, like myself and John Goodenough at 99 last year, and Bob Carver and so on, together with Kent Griffith, who's a young postdoc at Argonne National Lab. And we wrote a review about this story. And it's how it had gone from starting in the USA, and then work in Australia, then work in the UK, back to the USA, then Japan, and then the Brazilians come in with the mining. And this is a press release from last fall. So the Toshiba are really going to launch this. And it has two advantages. It has better capacity, volumetric capacity, so you can make a battery that packs more energy in a smaller space. And then in addition to that, it charges much more rapidly than the conventional ones. So that's shown in their sort of press release there. So let's go back to the timeline, just reminding you. So here's my lithium cobalt oxide. Here's the titanium niobium oxide. It's a long time. This is about 50 years before the light goes on, and you see you can do something useful with it. So this is a rather typical example of how things are done. And I wanted to just show some very recent stuff that we've done now, which concerns work. This is work that's currently going on, where we're repurposing. We're not deliberately trying to repurpose things, but we found something that was really interesting. And this is aluminum formate. And aluminum formate's been known since 1933. It's reported in a book by Gemelin in 1933. And then there was a bit of work on it in Russia in 1984, but without any structure or anything. And then 23 years ago, the manganese analog was made. And so we've been looking at this aluminum formate for CO2 capture. And this is a really interesting system. So we call it ALF, aluminum formate. It's always nice to have a quick acronym. So ALF has some very special properties. It's a bit like the zeolites I talked about earlier. It's got cavities and channels and so on. But what's special about it is that the cavities are just large enough to let carbon dioxide go into it, but they're too small to let nitrogen, for example, go into it. And this is an incredibly small difference. The difference between CO2 and nitrogen is like the difference that Linus Pauling worried about. It's a billionth of a centimeter. But this is the adsorption of carbon dioxide. This is at room temperature here. That's in blue. And that's the adsorption of nitrogen in brown at the bottom. So you get a selectivity of CO2 over nitrogen of several hundredfold. And so this is a magical system. We've looked at the structure of it using that technique that we'd worked on like 50 years ago, that Rietveld method, and we've looked at it with and without carbon dioxide in the channels. And this material has a fantastic affinity for carbon dioxide. Carbon dioxide is basically like a hand in a perfectly fitting glove. And so it loves carbon dioxide. But that's not the only thing it can do. And this is the interesting thing about it. Because of the size of that window, anything that's, say, smaller than about 0.35 nanometers will go into the cavity. And anything that's bigger than that is excluded because it's too big to go in. And so the difference between nitrogen and CO2 is like that billionth of a centimeter. And so we could separate anything above here from anything below, in principle. And so not only can we do the CO2 and nitrogen, but we can also do oxygen and nitrogen. And that becomes really interesting because this will absorb the smaller oxygen, but not the larger nitrogen. And of course, air has 20% oxygen. So this is the adsorption of oxygen into our material. No adsorption of nitrogen. So you can do an air separation into oxygen and nitrogen. And you know, during the pandemic, there's been a terrible shortage of medical oxygen because making medical oxygen is quite expensive. And there are different ways of doing it. You can do it cryogenically, which is expensive, but large-scale commercial process. You can do it with zeolites, but the zeolites absorb the nitrogen. So if you want separate oxygen and nitrogen, you'd rather take the oxygen out rather than try and take the 80% out. And so our material, with its affinity for absorbing oxygen, it is an absolutely super system. And it will do other things we don't need to talk about today. So the last cameo, and you were saying about convergence the other evening, Your Highness, at dinner. And this is a story of convergence. And I wanted to talk about the perovskite cesium lead iodide, which was first reported in 1893, before the discovery of X-rays. So people didn't know what the structure was. The structure was solved like 60 years later by X-ray diffraction. And it's got a perovskite structure, which my colleagues will know all about, and it's related to the sort of very hot topic of photovoltaics using lead iodide type perovskites. But this one didn't look to be particularly important until people found that you could make quantum dots out of it, like the quantum dots I was showing you earlier. High performance quantum dots for optoelectronic applications. The problem is that cesium lead iodide has 3 different forms, and only one of them is of any value because it's semiconducting. The other ones are yellow, and they're not semiconducting and they're useless. And so at room temperature, the yellow forms a stable one. And so you need to be able to stabilize the high temperature form. Over in Cambridge, while this was going on, we were working on some metal organic frameworks related to the zeolites we talked about earlier. So they're called zeolitic imidazolate frameworks. And Mohammed knows all about these. He's done a lot of work on materials of this type. And what we were interested in is because these frameworks, which are both organic and inorganic, because they are related to zeolites, which are related to silica, and silica makes good glasses, we thought maybe we could make glasses or amorphous materials out of this. And one of my students, Tom Bennett, discovered this in 2010 over in Cambridge, and we wrote an article. We published a lot of stuff on it, that we could first of all make amorphous versions of these ZIFs, and we explored their use for drug delivery, capture of radioactive iodine. So we have a US patent on the drug delivery application. But what's more important about these, in a way, is that if you can make an amorphous form, maybe you can make a glass out of it as well. But this would not be like normal glasses, like inorganic glasses such as silica or polymer glasses. This would be a hybrid organic-inorganic glass. And we succeeded in doing that, and I don't want to go into the details of how we did that, but other than say basically what you do, you take these materials, you melt them, and then and the trick is to melt them without decomposing them. And the melting and decomposition are very, very close. And then you quench them, and they're called melt-quenched glasses. And we made a whole series of them. And so this was work that's again done by my then student and postdoc Tom in Cambridge. More recently, we found that we can make composite with these, so we can take other things and put them in the glass. And Jingwei Hu, and I hope Jingwei's listening over in Brisbane in Australia, he basically led this tranche of work where he was able to make composites by embedding other materials into the ZIF glasses. And I'm not going to go through this other than to show that what you can do now with the ZIF glass, and this is the convergence, you can take that rather sort of tricky cesium lead iodide and stabilize the semiconducting form in it so that, first of all, it doesn't transform into the regular yellow form at room temperature, so you embed it in the glass. Secondly, it doesn't leach out the lead, which you don't want to happen. And so you can make these beautiful photoluminescent materials. Because it's a glass, you can make all sorts of shapes. And so these are the photoluminescent glasses. And here we're changing the color by changing the chemistry. You replace some of the iodine by bromine or by chlorine, and you can change the colors continuously and get an incredible gamut. So this was just published at the end of last year with Jingwei as the first author and Tom Bennett over in Cambridge, my former student, who discovered the original amorphous materials as corresponding author as well. So I just wanted to mention 2 things. His Highness and I went to Abu Dhabi the other day, and we, amongst other things, we went to this Artificial Intelligence Institute of the University for Artificial Intelligence. So the question is, what's the prospect of using that kind of technology to predict new materials? And there's a huge amount of interest in this, predicting new compounds with exciting properties using AI and ML. So does that put the synthesis of new compounds out of business, is a question. Well, the answer is, not really, because a computer can point you towards an exciting new composition, but it can't tell you right now how you'd go about making it. You still have, it's one thing to make it in the computer, another thing to make it in the laboratory. So there are, right now, very few examples of exciting new materials that were first discovered in the computer and then later synthesized. The other important point is that the computational tools like ML depend on the existence of a large amount of experimental data. And from all the experimental work that people all over the world have done over many, many decades of crystal structures and things like that, we have fantastic databases. And then the machine learning techniques utilize these databases for sort of optimizing their search for new possibilities. So it's important that we continue to add to those databases to help with the development and utilization of the computational tools. Without the experimental databases, they're limited. So my conclusions, Your Highness, are, first of all, synthesis of new compounds and new compositions of matter that can have exciting applications. The applications often come long after the initial discovery. I'm sure that the AI and ML methods have an exciting future, but they're not going to replace the work of being able to make things in the lab. So there's also going to be a role for exploratory synthesis to keep building a larger repository of chemical compositions so that future generations will have the materials that we've discovered today at their disposal for applications that come on. And the databases, of course, play a critical role in the AI. But finally, the point I wanted to make is that curiosity-driven science can have unexpected consequences. And that this curiosity-driven science, ironically, has been responsible for many of the most exciting discoveries that have been made in material science over the last few decades. And so it's very difficult to get away from the fact, when you look at the data, that curiosity-driven science has played a much bigger role than using design principles and things like that, just to be provocative. So finally, I'd like to have a couple of acknowledgements. First of all, to you, Your Highness, for your support for material science, and also for your personal kindness over the last 15 years, which is much appreciated. And then to my current and former graduate students, postdocs, colleagues at Oxford, Santa Barbara, Cambridge, and Singapore, who supported me and worked hard in my group over the last 50 years as an academic and a research mentor. And then finally to my family, last but not least, I should say, because I think my wife Janet hopefully is listening over in Santa Barbara, though she's saying, why don't you shut up, I think, because it's now 3 o'clock in the morning for her. But I'd like to thank Janet and the rest of the family for their love and unstinting support, because without that, I wouldn't be here with you today. Thank you very much.
Thank you, Tony. Would you be prepared to answer 1 or 2 questions, just brief?
Just 1 or 2.
So anybody have a question from the audience here? Anybody? No? Not here. And Natalie, nothing coming in over the wire? Okay, but I would like to emphasize what you said, and having run a materials lab like you, it was quite clear to me the people that make materials actually make things that God never made are really the kings and queens of this field. And oh, you have a question, sorry.
Tony mentioned that machine learning can't substitute for the synthesis part, but of course machine learning is being used for that too. Look at all the data sets there, right?
No, I'm aware that machine learning is being used to predict how you might synthesize something. You know, in our world of inorganic materials, I've yet to see how this actually plays out successfully.
No, I agree with that.
I would put it
So I know it's being done.
Slightly differently. Would you take a pill designed on a computer?
Probably a lot of them are.
Well, the FDA wouldn't let you, so thank God.
Yeah.
Okay, so, oh, please.
Vinayak.
You mentioned about the importance of fundamental blue sky research, and this is what we struggle for, as for me, for more than a decade, trying to convey this message for politicians. So what you probably have thought about this, what the future couple of decades would bring us in this perspective? Would it be harder or easier to persuade general public about the necessity of blue sky research, or will go into populism even further?
I think it's becoming more difficult, Andre. And it's becoming increasingly difficult because the funding agencies want you to tell them that you know what you're going to do. And if you're going to discover something entirely new, then you can't tell them exactly what you're going to do. So I think the only way of dealing with this is that you have funding, and then you tell the funding agencies, I'm going to do this, that, and the other, but you keep some of the funding on the side and do the kind of Friday afternoon experiments. But I find it rather depressing, but unless I could persuade, you know, the Prime Minister of Great Britain or the President of the USA to sit for an hour in front of me like His Highness has just done, and listen to the arguments, I think the chances of being able to do that are rather slim. Vinayak.
Amazingly inspiring and very captivating. Really enjoyed it. I know that you have all these beloved places that you've been, so I don't want you to contrast them, but can you give one word description of each of the location? What was the highlight from your perspective of this?
Oh my goodness, and I'm in danger of offending colleagues all over the world.
That's why I said you can say good thing about all of them.
Actually,
what I meant is creativity, collaboration, institutional support. You know, give us some context so that gives us a broader perspective.
They're all quite, you know, I've been at Oxford, Cambridge, Santa Barbara, Singapore, and they all have pros and cons. And, you know, if I had to pick one of them, and you said to me, Tony, you can only go to one place, spend your whole career there, I think I might go to Cambridge. See, I knew that I'd please somebody. I think I might go to Cambridge.
Because of Trinity as well?
Well, yes, and Vinayak didn't mention the wine cellar at Trinity, which is without peer. But all of them have been wonderful in different ways, and but we could talk about it later.
Yeah, I think so. So, okay, so I just would like to say a couple of words before we get to the main point of gathering here this afternoon. Your Highness, we're extremely grateful for your loyal support for past 15 years. It's been a fantastic journey, not only because of IWAM and your support for getting the very best people on the planet to come here, but also to watch RAK develop. This is part of the journey that I feel emotionally attached to. Perhaps Tony does as well. We're especially grateful to have your name associated with this Sheikh Saud International Prize for Material Science. This prestigious award recognizes somebody who's made significant contributions to the field of material science. We're especially grateful that you've allowed your name to be associated with this. And as a mark of respect from us who have been associated with you, this gives enormous pleasure. So thank you for that, sir. It is a prize that's recognized throughout the region here, and so that also has another special dimension. This year, the prize will be awarded to Sir Tony Cheetham. He's a research professor, as we know, in Santa Barbara, and distinguished professor at NUS in Singapore. Tony is, at heart, an inorganic chemist with an encyclopedic knowledge of the field. To me, it's mind-boggling the way he strings out these formulae. You know, I can remember telephone numbers, sort of, but this is like having a full encyclopedia of all the possibilities. Tony is truly one of the great material scientists on the planet, and as chairman of the board at RACCAM since the beginning, I really have enjoyed working with Tony. So it also gives me enormous pleasure to ask Tony to come forward, and perhaps Your Highness too, if you would. So.